So, welcome to this class on hardware security. So, we shall be continuing our discussions on power attacks. In fact, today we shall be looking the effect of power attacks on a new on essentially a different kind of primitive, like we have seen block ciphers, we have seen stream ciphers. In today's class we shall be looking at the effect of power attacks on elliptic curve cryptographic hardware. Like we have already discussed about the ECC hardware, we shall be trying to look at like the effect of SPA and DPA on ECC. And also in particular we shall be talking about a structure which is called as Montgomery's ladder to implement the elliptic curve, and we shall be discussing in the context of power attacks. Finally, we shall be discussing about Coron's blinding technique and doubling attacks. So, before we let us quickly recapitulate about power attacks. We already discussed this in several contexts, like there are two broad categories of power attacks, one which is called as simple power analysis, other one which is called as differential power analysis. In SPA, the fact that we were trying to kind of exploit is that the power or the power consumed depends upon the underlying operation which is being carried out. For example, in the context of elliptic curves, the power consumed for doubling operation is different from the power consumed for addition operation. So, if we can distinguish this in the power trace, if we can observe this distinction in the power trace, then that can lead to trivial leakage of the secret key. On the other hand, right, DPA or differential power analysis is more sophisticated, because it basically tries to exploit the fact that power consumed of this is essentially power consumed of the same operation is actually dependent upon the underlying data, and therefore, the dependence being more fundamental, even if there is a protection against simple power attack that can break against differential power attacks. So, therefore, we have already studied that in SPA, right, we basically work with like maybe one trace or maybe two trace or maybe few hundred traces, and trace is nothing but a set of power consumption across cryptographic operations. Like when we take we execute the cryptographic process, right, we are basically trying to measure the power consumed of the total device, not only like of the specific operation, but essentially of the total device, and that essentially is what we call as the power trace. So, we have already discussed about the power attack setup and how do we like accumulate these power observations. And but today, right, as we have already kind of probably understood, is that in general the lab setup is pretty expensive. So, here I shall be talking about an FPGA flow which you can easily set up for performing like fairly reasonable power analysis. Okay. So, this tool is basically based upon the Xilinx environment, but pretty much you can also try to find out equivalent components in other CAD flows. Okay. So, without loss of generality, let us try to understand our proposed methodology, which we can build up using a tool which is called as Xilinx XPower. So, Xilinx XPower and ISE are very popular tools of the Xilinx, essentially it is popular FPGA tools, and we try to develop a methodology using such kind of CAD tools. So, the idea is that first we develop a Verilog code, as we have seen that we are writing the Verilog code for our design. We synthesize the Verilog code using ISE tool, and this particular, after we have synthesized, the Verilog essentially gets translated into a form which is called as the netlist. Okay. So, next what we do is we take the netlist, and in the FPGA flow we basically map it into FPGA resources. The tool or the ISE tool does it for us, and the output is something which is called as a .ncd file. Okay. Now, this .ncd file is then passed to the place and route tool, again which is a part of the Xilinx tool chain, where specific locations on the FPGA are assigned, and the output is an updated .ncd file. So, you get an improved version of the .ncd file. In ISE, a flattened netlist can be generated after the map of the place and route tool. So, you just need to give these commands like generate post map simulation model. It creates a top level map underscore map.v file. So, again this is the top level flattened netlist, which means like all the hierarchies, like if you have in your design several modules, all the modules are kind of flattened to have the same level of abstraction, a single level of abstraction, and then you basically create a .sdf file. So, .sdf or SDF stands for the standard delay format. So, basically this particular file contains the delay or the parasitic delays of your circuit. So, you basically have like the various gate delay information, you have the routing delay information. So, pretty much the tool, whatever the tool is kind of predicting about your design, essentially is kind of noted down or kind of recorded in the .sdf file. So, now what we do is we basically write the or like add this to our test bench. We know that a test bench is essentially a component that we have in Verilog, through which we basically give stimuli to our design. We basically give inputs to the design and we verify whether the output is as expected or not. So what we add is basically we add these lines like initial, begin, and then inside that we write dot. Basically we dump the dot VCD file. So the VCD file basically is nothing but it contains the activity of each and every signal inside your design. Okay, so it basically contains the switching of your design. So you can kind of try to understand that the VCD file has got it measures the power consumption of the design, because there are switchings which are happening and those switchings are recorded in the .vcd file. So therefore, these are some commands which may work to download the .vcd file, and once you have this file, so which basically contains the activity, and therefore you basically have a measure of the switching activity, which is kind of a measure of the dynamic power of your circuit. And then what you can do is you can add a constant file which is called as .pcf file, and the .vcd file and the .ncd files are used as inputs to the xpower tool, and the xpower can be run from the command line. So therefore, if you run it then you will get a kind of profiling of power with time. So basically you get a dynamic simulation of the power consumption. So you don't get a monolithic value of power at the end, but you kind of get a power simulation which you can use as a representative of your power trace. Okay, so this can be a very I would say the in-house arrangement of doing power analysis, where you do not have access to sophisticated tools. Even otherwise, even if you have access to sophisticated tools, from here you can try to understand what are the points of interest of your circuit, and you can try to kind of focus on your real power trace at those points. Okay. So therefore, this proposed this is basically what it does is that this result which is produced by xpower is present in a text file which is say called topmodule.txt. It basically contains the instantaneous power consumption for the given test vector. If the .sdf file is also used in this simulation, then the power measurements use also the power consumed due to the glitches. So it is pretty accurate in that sense, okay, and pretty useful. So using a post, place and route netlist gives a more accurate power profile, and this feature is unfortunately disabled in the present version of ISE. So if you can go back and get some older versions, or maybe there are variants of this tool which you can try to still work with. So what we will do here is that we will again kind of look back at our elliptic curve processor, which we already designed in one of our previous classes, and this is the state machine that we left at which we left our elliptic curve hardware. So remember that we had some initial 3 clock cycles, but most importantly, when the scalar starts to get processed, then you basically try to see whether your key bit is 0 or whether your key bit is 1. So if your key bit is 0, then you just do the doubling operation, which is shown by the blue circles. That means you pass it through like 4 clock cycles, and then you basically get out of this point and you again come back to this state. So basically you go like D1, D2, D3, D4, and then again get back to D1. Okay. On the other hand, if your key bit is 1, then you basically go through the doubling states, then you go through 8 distinct states in addition in our state machine, and then you again go back to D1. Okay. So therefore, in this particular cycle, as you can see, there is a dependence in how you are basically migrating through the finite state machine depending upon your scalar bit. Okay. And that essentially is one of the reasons why we have a dissimilarity, and therefore we will see that this particular design is basically vulnerable against simple power attack. Okay. So the dissimilarity in this way is basically in the way that a 1 and a 0 in the key is handled, makes like the ECCP or the elliptic curve processor vulnerable to side channel attacks, or basically simple side channel attacks to be more specific. Okay. So let us see. So therefore, there are several leakage which are possible because of this observation. That is, for example, even from the perspective of timing. Okay, if you measure the duration of an iteration, then you will see that the duration of the iteration actually depends upon the key bit, because if the key bit is 0, then you have a shorter cycle compared to like a key bit of 1, where you are doing both doubling and addition. Okay, when the key bit is 0, you are only doing doubling operation, where you are spending 4 clock cycles. Whereas if you are doing addition, that means if the key bit is 1, you have 4 plus 8, that means 12 clock cycles in this particular operation. So thus measuring the duration of an iteration will give an attacker knowledge about the key bit. So if the attacker is able to understand this duration, then it gives an easy way of getting the key, because there is a clear dependence on that, there is a clear leakage. Okay. So each state in the finite state machine also has a unique power consumption trace. That means, as I said, that as we discussed, right, each state in the finite state machine is doing a specific set of operation, right. And as we discussed, right, one of the fundamental premise of simple power attack is that power essentially depends upon the underlying operation. So therefore every state has got a unique like footprint in the power trace. Okay. So monitoring this power consumption trace therefore would be interesting to look at, and we will see how we can use it to understand the secret key bits. Okay. So we will take this example and we will consider some power profiles. So these power profiles are got by our tool chain. Okay. So you can try to do the same thing in actual traces as well. Okay. So you will not get exactly similar profiles, but you will get like the basic idea will still be the same. Okay. So here is a power trace which has been acquired with an all 1 key, that means all the key bits are 1. Okay. Whereas in this case, right, it is all 0, which means like there is a MSB which is 1 followed by all zeros. Okay. So that means here I am only doing doubling operations, whereas here I am doing doubling, addition, doubling, addition, doubling, addition, and so on. So now you can see that there is a distinction between these two power profiles. You get spikes here, and these spikes are additional power consumptions which are due to the like the successive ones that you have in your secret key bit. Okay. So clearly just by seeing the power profile you can distinguish between these two keys. Okay. And that essentially is a leakage, because ideally, right, the power trace should not speak anything about the key. Okay. And it should be silent about the key. So immediately you can understand that this is a vulnerable design. If somebody is able to observe these power profiles, then there is a sneak that he or she gets into the secret key. Okay. So now what we will see whether we can develop a systematic way of getting the keys. Okay. And this is basically again a very simple technique or trick that we can apply, particularly for the design that we discussed. Okay. So we can of course develop more sophisticated techniques where we do template matching, power pattern matching, and so on basically, but we will see that even a simple trick can work. Okay. So basically what we observe is that the duration between two spikes in figure 7.1, that means figure 7.1 is essentially this figure, okay, where essentially you have got some spikes over. So the reason why you have like these spikes is because of addition. Okay. So basically, right, the duration between these two spikes is the time which is taken to do a point doubling and do a point addition, because you are doing both doubling as well as addition, and that is 12 clock cycles, 4 plus 8, that is 12 clock cycles. Okay. So if there are two spikes with a distance which is greater than 12 clock cycles, therefore it means that there are interposed zeros in between, right. So basically what I am trying to say is that suppose you have got like spikes like, okay, so okay, let me clear this up. 1 second. Suppose you have got spikes like, say these are your spikes, okay, which you are getting in your power trace. Okay. And these basically are comprising of like the instance between doubling and addition, that is you are doing both double, and you are also doing addition. Okay. So therefore, right, for double you have got 4 clock cycles, whereas for addition you have got 8 clock cycles. Okay. Now imagine that you basically observe this, you basically get two spikes, right, and you basically record that the time is t in between these two spikes. Okay. So if t is equal to like 12 clock cycles, you immediately know that it is like two ones, one after the other. That means there are no zeros in between, right. So on the other hand, right, if t is more than 12, that means if like that t is greater than 12, then you can understand that if there are like if there are n zeros in between, like n zeros in between, okay, so every zero will correspond to only a doubling operation, right. So therefore you can write that t will be in that case equal to 4nt, because like will be equal to 4n t. So t means the time period or the clock time period. Okay. So 4nt plus 12. Okay. So what I mean to say, I am talking about a key sequence where there are two ones and there are n zeros in between. Okay. So there is like 0 0 0 0 and there are n zeros. Okay. So that means if this is the time instance or time difference between them, then all the zeros will be doing a doubling operation, right. And therefore every doubling will take 4 into t, because t is the time period of my clock. So it will take 4 into t, and there are n zeros, so it will take 4 into n into t. Okay. So therefore, I will get a simple equation like this, okay. And if I know the clock time period, then if I know the value of t, then I can calculate the value of n, which is the number of zeros in between, right. So basically, I can pretty much just write this as n would be equal to t minus 12 divided by 4t, okay, and that is nothing but t by 4t minus so this will be plus 12t, because there are two so you will have 12t, and therefore t by 4t minus 3, okay. So therefore, right, this is the simple equation that we will be trying to adopt in order to get the number of zeros in between, okay. So now let us try to get back into our presentation and see that this is the formula that we use, okay. T equal to n equal to t by 4t minus 3, okay. So therefore, this gives me the number of zeros which are present and between two ones, okay. And the number of zeros between the leading one in k and the one due to the first spike can be inferred by the amount of shift in the first spike, okay. The first spike you can get by the number of zeros between the leading one in k and the one, because remember that we are always assuming in our algorithm that the first there is the leading one, right, and we are basically trying to process from the next from the bit after that, okay. So let us just try to apply this formula and see how we get. So for example, this is an unknown key trace, okay. So we have got an unknown observation, and the question is like, can we read the key from the trace, okay, because that is what SPA tries to do. So therefore, what we will do now is that we will see these spikes and we will time these spikes basically. So we will try to observe like what is the time difference between these spikes, okay. Suppose the attacker gets these spikes and looks at the x axis and finds out the time distance between the spikes, okay. And you can see very interestingly there are 9 spikes, okay. Here you can read out that there are like 1, 2, 3, 4, 5, 6, 7, 8 and 9. So there are 9 spikes here. So one is below actually, okay. So there are 9 spikes which you can observe here. Of course, you can understand that there will be noise, and sometimes you will probably miss 1 or 2 spikes, but here you can at least see few of them are pretty distinct, okay. Like at least these ones are quite distinct. So what I do is, therefore, what I observe first is that the distance between the spikes are not same. So you can see like the distance between these 2 spikes and these 2 spikes and maybe these 2 spikes are quite different, like this is like quite wide apart, right. So therefore, you are expecting that there are more zeros in between, okay. So therefore, we find that in our case the clock time period is t equal to 200 nanoseconds. So this is essentially the time the clock time of my processor, of my elliptical processor, and the first spike t1 is obtained at say some 3506th nanosecond, okay. So if there were no zeros before t1, then the spike would have been present as 2706th nanosecond, okay. So the idea is that there is a shift of 800 nanosecond, and the reason why you have got this shift is because there are 4 clock cycles. The shift is 800 nanosecond, which is equal to 4 clock cycles. Therefore, there is a 0 which is present before the t1 spike, okay. See, right, because if there is 1 0 present, then for that 1 0 you are doing a doubling operation, okay. That means even before this spike has come up, right, there are doubling operations, okay. So therefore, there are 4 doubling operations, okay. So basically what I am trying to say is that it is quite easy to obtain the time period between 2 successive addition operations, but how do you get the number of zeros before you get the first addition done, okay. So therefore, in this case we observe that it should start at 27606 and it starts from 3506. So there is a delay, there is a shift, and that shift is because of a doubling operation, okay. So now if you observe the clock cycles like 1, 2, 3, 4, 5, 6 and so on, you will see that the first time, the difference here is 2400 nanosecond, and 2400 nanosecond, if you plug into that formula that we discussed, right, this is the time interval between 2 spikes. So that means if I plug in like so this is the time 2400, if you plug in here like t by 4t minus 3, then this is 2400 divided by 4 into 200, okay, and that essentially will be 2400 by 4, right, is 600 divided by 200 is 3. So 3 minus 3 is 0, okay. So therefore, n stands to be 0. So therefore, we do it here and we find out that n is 0. So n is 0 means there is no between, there is no in between 0, okay, and therefore what you can infer that my initial key was 0 1, that is because of the first shift that I told about, like you have got one doubling followed by an addition, but then the next one, right, there is no 0, so that means this key is followed by this 1 is followed by 1, okay. Likewise, for the second time interval you get 2400, which again stands for 0, which means this one is followed by 1, okay. Then you get the next time difference is 4000 nanoseconds. So 4000 nanoseconds stands for 2. So you can again plug in the same into the same formula and you will get NES2. So NS2 means there is 1 is followed by 2 zeros and then there is a 1. Okay, so that means right now you can like pretty much read the entire secret key in this way, and you find out that the key is 0 1 1 1 0 0 1 1 0 1 1 1 0 0 1. Okay. And this stands for nothing but B9 B9, okay, and which is the actual key which has been used in this elliptic curve operation. Okay. So therefore, right, I mean you can see that SPA works in this case, because SPA essentially is a pretty powerful tool, because many of our designs, right, if I do it as a beginner, then I will probably not take care of this kind of vulnerabilities, and therefore our design, although it will be functionally correct, will be prone to this kind of attacks. Okay. So therefore, what we need to of course look into is how we can protect against these kind of vulnerabilities, and therefore the first resistance that probably we can think of is that let us try to develop an architecture where we do always add, that means addition is always done, rather than in the previous architecture where we were doing a conditional addition. Only when the key bit was 1 I was doing an addition, but now I will change my strategy and I will say that I will always do a dummy addition at least. Okay. So therefore, what I do is can be represented by this simple circuit. So I do a doubling, okay, and then I do an addition, but if the key bit is 1, right, then I will pass this addition, I will multiplex this addition, but the key bit is 0, then also I am doing an addition, but I am not using this addition, rather I am passing this input to the output. Okay. So this is essentially nothing but just simple multiplexer idea, right, but essentially this should prevent our SPA. Okay. So therefore, now again let us look back at our architecture. So this was our original old register block that we kind of designed. In order to make this modification, we have to change it in this data path. Okay. So what we do here is, now remember that we had 3 register banks. Now along with these 3 register banks, we add an additional register bank. You can see that now there are 4 register banks. So this register bank is basically storing the result of after the doubling operation. So whatever is coming after the doubling operation, I am storing that in a temporary register file. The idea is that if the secret key bit is 0, right, then essentially I will take only the output of from this register file. Okay. So therefore, the addition which is happening even after, even if the key bit is 0, is something which I need to ignore, because that's a dummy addition operation. That is, if I take that, then I will get a wrong result. Okay. So therefore, now you will see that because of this like register that we have introduced here, dummy register you can say, which is storing the value of your or rather let me say it is a temporary register which is storing the value of your doubled operation or doubled output, essentially needs also like a multiplexer at the input, and also needs few additional lines to get the result out in the output port. Okay. So therefore, these multiplexers are also little bit widened up, because now you need also these register outputs to be to be channeled outside. So therefore, right, there is a cost that you need to pay, I mean essentially, but at the same time, right, if you observe the power profile now with this change, you will see that those clearly distinct spikes are now not present. Okay. So pretty much you will see that now every you get addition at every time instance, and therefore this you can see that even if I change the key, the pattern will look roughly the same. So at least to the visible eye, you will not be able to kind of easily demarcate and try to see that there is a dependence. Okay. So therefore, the right hand side power profile shows a blunt profile, and therefore it is more resistant against simple power attacks. What is the price that you pay? Of course, you have to pay a price, because there are some additional hardware you have used. So in this case, this is a transformed FSM. So now you see that those conditional lines are gone. Rather, like whenever you get into this doubling chain, you ensure that you do the addition and then you get out. Only then you are not using that result. Okay, you are using the result of the output of the doubled stage. Okay. So the total clock cycle is therefore always 12. So in a way, this is also timing attack resistance or timing resistant, because it is always taking the same number of clock cycles to give you the output. So, okay, the time essentially is not leaking about the key. So if you see the footprint on hardware, you will see that there is a blow up. That means there is a diminution in the frequency, there is an increase in the slice, there is a like the increase in the number of clock cycles, but that is the price that you pay for this security, So now we will see how we can so now we will basically consider about how we can make it protected against further power analysis. For example, we will see that even though it protects against simple power attacks, this is not secured against differential power attacks, which basically tries to exploit the fact that power consumed depends not only upon the operation, but also for the same operation it depends upon data. Okay, and therefore this design would be still vulnerable against DPA. So in order to protect against DPA, we need to do something more. So that we will see in the next class. So thank you for your attention.